next, ionic compounds. These guys are different from molecular compounds because instead of being made of atoms, they're made of charged ions. Okay, so we're talking about positively charged ions, negatively charged ions, or if you want to use the super sciencey terminology, cations and anions. Ionic bonds form in ionic compounds when an electron is transferred, okay, and it gets transferred from a cation to an anion. If we compare this to how bonds are formed in molecular compounds, those bonds are formed by sharing electrons. So ionic bonds form in ionic compounds with a transfer of electrons. Covalent bonds form in molecular compounds by sharing electrons. Okay. When we write formulas, or when we're talking, I guess just generally talking about ionic compounds, it's really important to know, yes, these compounds are made of charged ions, positive charges, negative charges. Okay. However, compounds must be neutral, which means they have overall no charge. How does that happen? Well, the positive charge from the cation has to be balanced out by the negative charge contribution made by the anion. How does this all work? Let's look at it. 4 steps to writing formulas for ionic compounds. Okay, you'll need your periodic table, unless you have it memorized. First thing we need to do is we need to write the chemical symbols for each element, okay, with the metal written first. Let's make this a little bit more sciencey. Let's go with the cation written first. And then let's say, I'm just wordsmithing here, fam. Okay, important to recognize that these are ions. Why? Because step 2 has us looking at the ionic charge. So let's edit step 1. Write the chemical symbols for the ions with the cation written first. Then, step 2, write the ionic charge above each symbol to indicate the stable ion that each element forms. Oh, I see where I was going with this. Anyways, I digress. Step 3, determine how many ions of each type you need so that the total ionic charge is 0. Step 4, write the formula using subscripts to indicate the number of each type of ion. And here we also see 1 as a subscript not being used. Now, we are going to do a little bit of a shortcut, okay? And we are going to, instead of doing figuring, okay, we are going to do something called, I wrote that the wrong way. Oh, well. The criss-cross rule. I've also heard it called, I think I like this one better, actually. Cross and drop. It sounds like it should be a TikTok dance move, the old cross and drop, okay? If you figure out what that looks like, you send it to me. That's what we're going to do with steps 3 and 4. We just replace it with a bit of a shortcut. Why not? Work smarter, not harder. Am I right? Okay, now, let's do some practice. So what we want to do here with these 4 examples is we want to figure out what the formula for the ionic compound formed between these cations and anions would be. First up, lithium and fluorine. Step 1, write their symbols as ions. So using our periodic table, we can see that lithium ions have a +1 or 1 positive, however you want to write it, charge. Then fluorine, which now actually is fluoride ions. Oh gosh, sorry, I touched the board accidentally. I'll never do that again. form ions with a 1 minus or minus 1 charge. Okay, I think we've just done steps 1 and 2. Okay, so then steps 3 and 4, cross and drop. What does that mean? Well, what we're going to do is we're going to look at the number only, not the sign, not the positive, negative, just the number, just the ones here. And the number, the number of the charge on one ion becomes the subscript on the opposite ion. So here's the crossing. This 1 on lithium becomes the subscript on fluorine, and this 1 on fluorine becomes the subscript for lithium in the chemical formula. So what we could write is Li, and there'd be one of those, F, and there'd be one of those. That's the crossing and the dropping. Kind of hard to see in this example because they're both exactly the same, but it will be very apparent in a couple of other examples that we do. Now, I know some of you out there are saying, whoa, 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 lady. You literally just finished telling us that we do not need to have 1 written as a subscript. And you, friends, are exactly correct. Li1, F1, take back those fractions of a second of your life. Don't write the ones. Li1, F1 just becomes LIF. Final answer. I'll box it. Final answer. Okay. What about magnesium and bromine? Again, let's start from the top. Let's go through these steps very mindfully. Someday, perhaps, if you really want to be and you want to put in the work, you'll be a chemistry expert and you won't even need to do these steps. But for right now, when we're just starting out our journey into chemistry and ionic compounds, we will go through all the steps very mindfully. So, magnesium, group 2 on the periodic table. It has a charge of 2+. Bromine, as an ion, we call it bromide, and it's Br, and it has a 1- charge. Okay, so here's what we're doing. Cross and drop, right? Just the numbers, not the signs. So you'll notice if we just jump back here to LIF, there's no charges, no positive, no negative, written for a compound. If you have charges in there, that's incorrect. Wrong. Okay? So, back to magnesium and bromine, cross and drop. Boom, boom, boom. This 2 that was the charge on magnesium goes down to be the subscript on bromide. And this 1 that was in the charge on bromide crosses and drops to be the subscript on magnesium. So we would get Mg1, Br2, and then we would say, hey, we don't write the ones. It's just going to be Mg, Br2, like that. Some of you might be thinking, oh, do I have to show this step? No. Okay? No, you don't have to show that step. But if you are working to have a solid understanding and you need to do that step on like a scrap piece of paper or in the margin or wherever, do that step. I won't be looking for it though. Okay, I'm going to go through calcium and phosphorus, cesium and oxygen. If you're feeling like, hey, I've got a pretty solid understanding, pause the video here. Try these 2 on your own. Come back, join us. Calcium and phosphorus. Calcium, Ca, has a charge, forms ions with a charge of 2+. Phosphorus, P, and when it's phosphide, it has a 3- charge. Cross and drop, fam. Boom. So now when we write the formula, we've got Ca, and then we have to indicate that we've got 3. Where did the 3 come from? It came from the charge on phosphorus. P, we have 2 of them. So Ca3P2. Last one, cesium and oxygen. Cesium, found in group 1, so it forms ions with a 1+ charge. Oxygen forms oxide ions, has a 2- charge. Cross and drop. CS2O. Okay. So that's kind of like level 1, intro level. Does this get a little bit more challenging? Yes, it does. Let's look at perhaps how. Oh, there's a slide about the crisscross rule. I do want to go through one of these on this page with you, on this slide with you guys, just to talk about reducing. Okay, let's do this example of barium sulfide. So there's the name of the compound. The compound's name is barium sulfide. All right, so using our periodic table, barium forms ions with a 2+ charge. Okay, it's in group 2. Sulfide, which is in group 16, forms ions with a 2- charge. Okay, cross and drop. We come up with Ba2S2. Ba2S2. However, the kind of formulas that we're writing are called empirical formulas. And with empirical formulas, what we do is we show the lowest ratio of anion to cation that we need to get an electrically neutral compound. So it's the lowest ratio. Right now, as we have it written, Ba2S2 is showing a 2:2 ratio, 2 bariums to 2 sulfurs. Can we simplify? So we always have to ask ourselves that at the end of writing the formula. Hey, can I make this any more simpler? Can I simplify this ratio of cation to anion? A 2:2 ratio simplifies to 1:1. So instead of saying 2 bariums and 2 sulfurs, I could say I've got 1 barium and 1 sulfur. And isn't that nice? Because I actually don't have to write a subscript at all. Because we don't write once, right? So that will be one last step you need to take care of with this cross and drop or crisscross rule, is that you will need to double check that you have simplified your ratio of cation to anion. Now, if that seemed too easy, maybe it didn't. So, this is challenging. Again, with the more practice that you get, the easier it becomes. Now we want to introduce to you this idea of multivalent metals. I want you to take a look at your periodic table and look in the middle. Okay, so I'm talking like groups, I don't know, 13, 14, all the way up to group 12. There's quite a few metals in there that have different ion charges listed. So some metals are able to form more than one kind of ion. So if we take a look, oh, that's already on there. Copper as an example, right? If we look, copper can form ions with a 2+ charge, or it can form ions with a 1+ charge. To distinguish between the different ions, we use Roman numerals to indicate the ionic charge when we're writing the name of the ion. So let's look at these examples we've got written on here, copper 2 and copper 1. Remember, when there's no number written, we assume it's a 1. So if we're talking about this Cu2+, what is its name? Its name is copper 2, and here's how we write the 2. That's Roman numerals, okay? Hopefully you know your Roman numerals up to 5. If not, please make sure you look into that, and that could be another piece of information you add to your periodic table. Now this copper with a 1+ charge, here's the exception to, hey, we don't like to write 1s when there's only 1 of something. We will need to indicate when it is copper 1 that we are talking about copper 1. So we do that again with Roman numerals. Okay, copper 2 and copper 1. Hey, you know where we don't do this? We don't do it when the metal is not multivalent. So for example, if you're looking at like sodium, number 11, atomic number 11, only forms ions with a 1+ charge. We don't call them sodium 1. We call them sodium ions, period. Okay, we don't need to indicate when we're dealing with ions that only form 1 possible charge. Okay, don't need to specify. When we're dealing with these multivalent metals in the middle of the periodic table, yeah, we do need to specify. So let's talk about this other guy, Sn. Where's that? What a weird one, okay? If you haven't found it, it's atomic number 50, and turns out that Sn is tin. Weird, but okay, we'll go with it. Lots of these atomic names come from, or the names of elements come from different languages. So French, Latin, Greek, etc. I don't know about tins. I would suspect it's probably Latin. But again, that's nice to know, not need to know. Okay, tin 2+. We could call a tin 2 ion. The other option is 4+, so we'd call that a tin 4 ion. Really important that when we're dealing with multivalent metals, in the name, we are indicating which one we're talking about. Okay, that's a must. That's a rule. Next little wrench is this idea of polyatomic ions. Generally, in periodic tables, there is another chart added on top of the periodic table that lists lots of the common polyatomic ions you will run into in your chemistry career. So these do not need to be memorized. And if you're looking at your table of polyatomic ions and seeing how many are there, you're probably very thankful they don't need to be memorized. When we write the formula for these ions, my hot tip for you is treat each polyatomic as a single unit. We'll see what that looks like in just a second. But just the way you dealt with like chloride ions, okay, as one thing, we're going to treat polyatomics as though they are just one thing, even though they are ions made of more than one atom. And then last rule is that when we have more than one polyatomic ion present in a chemical formula, we have to enclose the whole polyatomic in brackets or parentheses. Okay, so we need to make sure that we're indicating that we have more than one of the whole polyatomic. Let's do some examples. I'm going to change these examples so we can, not all of them, so that we can also take a look at the idea of multivalent metals. So let's go with, I'm going to change this one here. Iron 3, and then, oh my gosh, making decisions is hard. Okay. Okay, I've got it. I'll just change that one. Okay, here we go. We're going to follow, guys, the exact same rules that we just followed previously. Okay, we're only introducing concepts of polyatomic ions, multivalent metals. So let's look. Our first compound is called iron 3 nitrate. Iron 3 nitrate. We go through the same steps. Step 1, write the formulas for your ions. So we've got our iron 3 ion. It's actually kind of nice when they put which ion you're dealing with, because then you don't have to necessarily look up the charge. You know it's going to be 3+. And then we've got this thing called nitrate. Well, that's not on the periodic table. Okay? So make sure you know there's a difference between, let me tell you all the things, nitrate, nitrite, nitride, okay? Those are 3 different things. Nitride is nitrogen when it forms an ion. We are clearly not talking about nitride. We are talking about nitrate. Nitrate is a polyatomic. If you look it up on the table of polyatomics, you'll see that it's NO3. So again, poly meaning more than one atom making up this ion, and the whole nitrate ion has a -1 charge. So NO3 altogether, -1. Some students that I've taught prefer, even at this stage, to use brackets. So they're just going to put the whole polyatomic in bracket. That reminds them to treat it as a single unit for our cross and drop. Okay? Again, taking a look at just the numbers in the charges, not the signs. This 3 from iron will go to the outside of the bracket on nitrate, and the 1 from nitrate drops down to the iron. So, what do we get? Fe, and you can, if you want to write the 1, you can go through that whole step, and then brackets, NO3, brackets, 3. Think about what this would look like if we didn't write the brackets down. It'd be weird. Something like that. That's weird. Okay, NO33? No, that doesn't make sense. Okay, we need to enclose the brackets. This way that I've written here in green does not show that I have 3 nitrates. Okay, I need to show that I have 3 nitrates. This shows that I have 1 nitrogen, and depending on how you read it, could be 33 oxygens. That's not nitrate. Okay, that's why we need the brackets if there's more than 1, which here there is. Okay. Let's do magnesium phosphate next. Magnesium 2+, phosphate. So again, just to keep you on your toes, there's a phosphate, there's a phosphite, there's a phosphide. Make sure you're using the right one. If it ends in "ide", more often than not, I can only think of like a couple of exceptions, it's an ion from the periodic table. So anything that ends in "ide" is an ion, a monoatomic ion, okay, so off the periodic table. Phosphate is PO4 with a 3- charge. Again, this is in your table of polyatomics, so make sure you're looking there. I've put the brackets around it already because I can see there's going to be more than 1. Okay, formula time. Mg, we need to take the 3 that we crossed down from the phosphate. There it is. And then we have 2 phosphates. That comes from the 2 in the charge on magnesium. PO4 in brackets because we have more than one, and with a 2 on the outside. Okay, I'm going to do these next two, nickel 2 hydroxide, I've changed it, and ammonium chloride. If you feel like you have a solid grasp, pause the video here, jump in, join us, see how you do. Nickel 2 hydroxide, so nickel with a 2+ charge. Fun. Hydroxide, now here's one of them that ends in "ide" but is still a polyatomic. I see a lot of students thinking that this is hydride, like it's just an H with a 1-. That's not the case. So look in your table of polyatomics, you can see that hydroxide is OH, I'm putting that in brackets, and it has a -1 charge. Okay, cross and drop. And what we get is Ni, and then in brackets, OH, 2. Nickel 2 hydroxide. Last example, ammonium chloride. So ammonium chloride kind of demonstrates, I put this on here very specifically, almost like I know what I'm doing when it comes to teaching about ionic compounds. Okay, ammonium is a cation that is a polyatomic. So ammonium is not a metal. Don't look for it on the periodic table. Ammonium is a cation, but it's not a metal. It's a polyatomic. So we look in the table of polyatomics and we see that ammonium as a cation has a formula of NH4 and that has a +1 charge. Okay. Chloride is chlorine with, when it forms an ion, a 1- charge. So again, cross and drop. Now we can see here, I'll do this. NH4, I've put in brackets, there's 1, Cl, there's 1, that's a 1. Okay, remember how we don't write ones, so I'm going to change this formula and make it more accurate. Okay, we also don't need the brackets when we have just one polyatomic. Okay, so what this becomes, since I only have the 1 ammonium, I'm just going to write NH4Cl. That is the formula for ammonium chloride. So no subscripts, because they're both 1s, and then no brackets needed, because I only have 1 polyatomic. All right, you know everything you need to know about how to write formulas for ionic compounds. I would suggest you do many hours of practicing just to kind of reiterate these concepts, figure out all the different little tricks, things you need to watch out for. We can also write the names of ionic compounds given the formula. So, things to remember. The name of the metal always comes first, followed by the name of the nonmetal, ending in IDE. That's when we're dealing with those monoatomic ions that we find on the periodic table. A more scientifically accurate way to say the same thing is that the name of the cation comes first, followed by the name of the anion. And if you're thinking cations and anions, then you're already thinking of those nonmetals having endings of IDE, so we don't need to think about that further, hopefully. To watch out for, those multivalent metals, pesky little buggers. If the metal or the cation, well, it would only be a metal cation, could have more than 1 charge, i.e. it is multivalent, we indicate the charge in the name of the compound. by using Roman numerals. What's that look like? Let's find out. Okay, this first one on here, some of you guys probably already have the name written down. Yes, fantastic, but let's make sure we're going through the process. So we're going to take a look at our formula, NaCl. Name of the cation. So cation is always written first in the formula and the name. So our cation is Na. If you're not sure what that is, you can look it up on the periodic table. It's sodium. And sodium is not a multivalent metal, so I don't need to write down with Roman numerals what the charge is. I just say sodium. Cl is my anion. It's chloride. Okay, so I just write that name. Space between the two names. Ta-da! It seems so easy. Let's see if we can step it up a little bit. So sodium chloride, first one. Second one, CaSO4. Wow, I tend to see lots of creativity coming through in naming compounds like this. This is an area where I don't want you to be creative. I want you to follow the steps for writing the proper name. So CaSO4, we have to recognize that all ionic compounds are formed from one cation, one anion. Doesn't matter how many different elements are in the formula. If it's an ionic compound, there's only one cation, only one anion. Okay? So your job, maybe when you look at a formula that looks like it might be a little bit more complex like this, is to figure out, okay, what's the cation, what's the anion? Hopefully you can recognize calcium as your cation. That means everything else left must be your anion. So SO4 is your anion. I hope that you look at that and you say, it looks like a lot of atoms in that. In fact, a lot of atoms would be called polyatomic. So I hope that you recognize that this is a polyatomic ion. Okay, so the only difficulty in this particular example will be recognizing what's your cation, what's your anion. Once you have that piece of information down, we take a look. Ooh, calcium. That's my cation. Calcium's not a multivalent metal, so I just write calcium. I don't write the 2. Okay. Then my anion. I look in my table of polyatomics and I write down exactly what it tells me. You can find the anion SO4. It has a 2- charge, but we're not really worried about that right now. What we are worried about is that it's called sulfate. Calcium sulfate. Those two are pretty straightforward. Then we get into our last 2 examples, and you'll notice that these 2 formulas are quite similar. They both involve Sn, which is tin, and O, which is oxygen or oxide. Okay? If you look on your periodic table, find tin, atomic number 50, you'll notice tin is a multivalent ion. So we'll need to make sure that we know which tin we are talking about. Our options are 2 or 4. That's it. Okay. Well, how will we know? Well, we kind of have to maybe work backwards. How did we get this formula SNO? How did we get this formula SNO2? Okay. Well, we know if we worked our way backwards through the formula, Sn has a positive charge. It's either 2 or 4. We're not sure which it is at this stage. O, however, is not multivalent and can only have a 2 negative charge. Recognizing, remember that cross and drop. Boom. And then whatever number this is would cross over here. And it looks like, based on the formula we've been given, that these 2 subscripts that we would have written here and here canceled each other out or simplified to give us a 1-to-1 ratio. Well, what could we put we know that we would write SN2O something from this charge on tin. Well, what would we put in this spot that would reduce tin and oxygen to 1-to-1 ratio? It would have to be a 2. That's the only way we're reducing to 1-to-1, if that makes sense to you guys. So working our way backwards through that, we can say, ooh, okay, this must have been tin 2 oxide. Okay. Compare. That might be a little bit confusing. Let's compare with SnO2. So again, going through the same process. Tin has some sort of a positive charge. Oxygen, whoa, out of control. Whew, lost it for a second there. Oxygen has a 2- charge. Again, we would do the old cross and drop. And we would come up with SN2O something. And that something has to reduce with the 2 to give us a 1-to-2 ratio. Well, what would reduce to give us 1 tin and 2 oxygens? Well, a 2-to-4 ratio would also reduce to a 1-to-2 ratio. Okay, therefore, mystery solved. This tin must be tin 4. Be on the lookout for those multivalent metals. They are tricky tricksters. I don't want you to get too stuck on them. Okay, so just be paying attention. Is the metal that you're dealing with, is it just got one option for its positive charge, or does it have more than one, in which case you have to figure out which one you are talking about.